This following video is going to explain what a decision table is in terms of computing. This links in with a topic on section 1 problem solving. A decision table is a precise yet compact way to model complicated logic. The principle goes back to ancient Babylon times, where rules for multiplication were baked into clay tablets. It is a way to model if, then, else constructs. And decision tables, they can help if there are lots of different actions dependent upon the conditions. Decision table layout is shown as follows. It's just a simple way of displaying what actions are to be taken when certain conditions are met. In here, this is where we put the actual conditions themselves. If you think of some programs we've been doing at the moment, conditions may be mark is greater than 80, sales equals Y, age is less than 16, age equals 17, if number is greater than 5. So these are all conditions. That's what we put there. In this section, this is where we put the actions, e.g. output well done, output merit, output you're not allowed, output you're not old enough, output you don't have insurance. So these are all the actions that take place. They don't always have to be outputs. Some of this could be calculations. The conditions entries, this is just indicating if they've been met or not been met, so this will be by a Y or an N, and the actions is usually represented by an X. Let's look at an example. Very simple, straightforward example. A mobile phone service provider will allow a person to be a subscriber to their network provided that the following conditions are met. So they must have a bank or a building society. They must have lived at the same address for at least a year, and they must be a homeowner. And you must meet all them conditions in order to be able to have the one action, and that is subscribe. So let's look what this looks like as a decision table. We can see we've got our three conditions there. They have a bank, a building society account, lived at the same address for more than 1 year, is a homeowner. And we've got every combination associated with these. All of them are true, 2 of them are not the third, first one and the third one, second and the third, just one of each and none. Notice with 3 conditions there are 8 combinations. 2 to the power of 3 equals 8. This links in with the magic binary numbers that we've discussed before. Now going back to the example, it says that all the following conditions must be met. So therefore the only way they can subscribe is if all of them are yeses, and it's easy to see that the rest cannot describe. So they are the 2 actions. We could quite easily model that as an if statement. And what we're going to get across here we can say if bank equals yes and lived here is greater than 1 and homeowner equals yes, then output they can subscribe, else output you can't subscribe. So that shows a an if statement associated with that problem there. And the whole idea of a decision table is to model complex if statements. We can see it's got this condition and another condition and another condition. So that is modelled through that example. Here is an example of a decision table found in a printer manual. So this has got a series of conditions. Printer doesn't print, a red light is flashing, printer is unrecognised. And it's got some rules to follow. So if the printer doesn't print, there is a red light flashing and the printer is unrecognised. First thing it says here, check the USB cable, ensure the driver software is installed, maybe check and replace ink cartridges. So there's several actions and rules that can be followed. I'll give you a few moments just to pause this and have a look through those. Sometimes with decision tables we end up with impossible rules. So sometimes there's no point in writing down all the rules. For instance, if you are going to choose from the following, now these could be say videos here, these could be movies online, and it could be if you hire 1 to 3 movies, you get them at a certain price, say £4 each. If you hire 4 to 7, you might get a discounted price of £3.80 each. If you hire 8 or more, you might get them at a discounted price of £2 each. But there's no point in putting all the rules, e.g. yes, 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 because it's impossible to hire 1 to 3 at the same time as you're hiring 4 to 7. So we would just put, in this situation, no, 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 yes, no, 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 yes, no, 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 yes. So there'll be 4 rules. Sometimes we get redundant rules. These are rules that may be combined together. If you combine rules, then what you're saying is that whether the condition is met or not, the action will be the same. If it can be a yes or no, you put a dash. So look at this one here. This is to do with the traffic lights. So we're showing the red light is showing, the amber light is showing, the green light is showing. If we've got all 3 showing at the same time, we'll stop and we'll call the traffic police. If the red and the amber light are showing, then we know we're getting ready to go. If the red and the green light are showing, then we'll stop and call the traffic police. If the amber and the green light are showing, we'll stop and we'll call the traffic police. If just the red light is showing, we'll stop. If the amber light is showing, we'll stop. If the green light is showing, we'll go. If none of the lights are on, we'll stop and call the traffic police. With redundant rules, we start to have a look if there are any rules where we can see that everything is the same apart from one condition and the actions are the same. So in the case of all these, I've highlighted 2 there. This one, yes, 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 with a stop and call traffic police, and this one, no, yes, yes, with a stop and call traffic police. Basically, it doesn't matter if the red light is on or off. If the amber and the green are showing together, regardless of this, we will stop and call the traffic police, which means that can be combined together into one single rule, and that's how that is represented. This therefore says it doesn't matter if it's red or not. If these 2 are showing, we're going to do the following. Looking at the rest, we can't do anything else. We've got that condition there is the same, those actions are the same as those actions, but that's 2 changes, y and n, so that you can't combine them together. The same with you can't combine that and that, because despite the 2 yeses, them 2 are different and them 2 are different. So once you've removed all of the redundant rules, you may be able to take the table a stage further and reduce further redundancies. And for your final decision table, you need to aim to eliminate both impossible and redundant rules. Here is a decision table, and this is what I'm going to leave you with. That's got 3 conditions on there. Age is greater than or equal to 25, you have a clean license, and you have a blame-free accident record for at least 2 years. There are 3 actions: normal premium, loaded premium, and insurance refused. What I would like you to do is, prior to the lesson, to have a go at solving that decision table and removing any redundancies, drawing out each step that you go through, ready to use for the start of the lesson. Okay.